Okay, this video is about motion word problems. So before we begin, what I want you to do is to draw a particle model, position time graph, a velocity time graph, and acceleration time graph of the following scenario. So you're driving in a school zone at 6.7 meters per second for 5 seconds. After passing the zone, you increase your speed to 15.7 meters per second in 3 seconds. Go ahead and pause the video and see what you get and compare it with mine. Okay, so here's what I have here. I have my particle diagram. Now, it's not necessary to put in the numbers there. We're just using our particle diagram to kind of visualize what's going on. And you can see here for the first 3 seconds, we've got the same spacings between each particle. And so therefore, I should have a constant slope in the first 5 seconds here. I meant 5 seconds here. Okay, now, after the 5 seconds, then you can see that the acceleration is getting larger, so therefore my curve is going in here, and then I've got 15.7 meters per second as my final slope in my position time graph. So I've got a slope of 6.7 on the position time graph, therefore I should have a velocity of 6.7 meters per second. Then I have an increasing tangent line, remember that from the last video, so therefore my velocity is going to increase until finally I get to 15.7 meters per second here after 8 seconds, and that's what my slope should be here on my position time graph. Now, it's not necessary in the warm-up to put in 3 meters per second or just 3 meters per second squared, but I put it in here anyway to kind of remind you that the slope of our velocity time graph, this 3 meters per second squared, is the acceleration from 5 to 8 seconds of 3 meters per second squared. Okay, so in this video, today what we're going to do is complete word problems mathematically and graphically. I'm going to show you a couple of ways to get to the same answer when you're doing a problem, whether it's going to be on an exam or a quiz. This should help out. Okay, so I'm going to give you a couple of scenarios here, and for each one of them, you're going to do just like we did in the warm-up. I'm going to draw a particle model, position time graph, velocity time graph, and acceleration time graph. And what I want you to do, though, is to label the important quantitative points on each model and graph, just like I showed you. But you don't necessarily have to measure, and everything doesn't have to be to scale. It's just to help you out to figure out the problem there. And then I want you to try to answer the question using your graphs or using the equations that you have for motion. So let's start off with the first one here. So we got a toy car is traveling at 0.5 meters per second for 10 seconds, and then the battery dies. How far did the car travel before it died? All right, so pause the video and see if you can come up with all 3 graphs to help you answer the problem. Okay, so here's what I have. I've got my particle model. The positions are the same spacings throughout. But look at my position time graph here. I've got a slope of 0.5 for 10 seconds, and then it goes to a flat line there. And for my velocity, I'm going to have a 0.5 meters per second for 10 seconds, and boom, then it's going to die. However, for the entire time, I have no acceleration here in the car, so therefore it's going to be a flat horizontal line the whole time with an acceleration of 0. And what I'm going to do is I'm going to use these 2 graphs, my position and my velocity time graph, for my answer. The first one, my position time graph, we can create a mathematical model. And if you've watched the other videos that I have up there on YouTube, you're going to find that you've already done this a few times, and it's not that hard to do it with this data here. And we're going to create that mathematical model to help us answer the question. We're also going to use the velocity time graph in this area here under this curve to tell us a little bit more about the answer there. Okay, so we've got a toy car, and here's my position time graph. And on my position time graph, I've got a slope of 0.5 meters per second, and the graph is going to go until 10 seconds here. So I'm going to turn this into a mathematical model, y equals mx plus b. So here it is. I've got my y, and that's equal to my m, which is going to be my slope of 0.5 meters per second. X, in this case, it's time in seconds, plus b, because the graph goes straight through the origin here at x equals 0. then that's going to be my plus b here. Okay, so go ahead and put in 10 seconds in for my time here. And what you notice here is that I've got a second here and a second here in the denominator. Using dimensional analysis, those two can cancel. And what I'm left with is just these two terms here. But look at this term here, x naught, or my initial position here. That's at 0. So I can get rid of that one as well. And so what I'm left with is 0.5 meters times 10, or 5 meters. Now let's take a look at my velocity time graph. Okay, so I've got a velocity time graph. And one thing I can tell you is that if I were to calculate the area of this rectangle here, what I would get is height versus width. My height versus my width. And so when I do that, I get my meters per second times second. And if you draw this out on a piece of paper, you'll figure out that the seconds cancel, and I'm left with an answer in meters, which in turn tells us that the area under this curve here is my displacement. Okay, so let's take a look. If I were to go ahead and take the area of that box, it's going to be my velocity times time. And the seconds we're going to cancel here, leaving me an answer in meters, which we know is displacement. So if I go ahead and put in the numbers, I get 0.5 meters per second times 10 seconds here. The seconds will cancel, giving me the same answer I had with the other graph, 10 meters for my displacement. Now the third and final way we're going to do this is with the equation itself. So here it is. We've got our velocity equation. It's equal to the change in position over change in time, or delta x over delta t. From there, we can go ahead and write that out as x1 minus x naught, or final position minus initial position, over final time minus initial time. And if I look at the problem here, I've got an initial position of 0 meters. And if I start my timer at the very beginning of the problem, my initial time is also going to be 0. So I can get rid of those two terms right there. They disappear. And so what I'm left with is I've got my velocity, or 0.5 meters per second, is equal to my final position divided by the time in seconds. Multiplying both sides by 10 seconds, canceling my units, what I get is 5 meters for my position. So let's review here. I've answered the question 3 different ways, and all 3 ways are going to give me the valid answer that I want. I'm just doing it differently. With the first one, the position time graph, I'm going to create a mathematical model of this linear data here. For my velocity time graph, I recognize that the area under this velocity time graph is my position, or displacement. Or I just simply plugged and chugged with the equation there and did it the old-fashioned way. So let's try another problem here. Okay, so I've got a car and it's stopped at a stoplight. When the light turns green, the car accelerates at a rate of 5 meters per second squared for 2 seconds. What's the final velocity of the car? Pause the video, see if you can come up with the particle model, position time, velocity time, acceleration time. Put in the appropriate numbers in your graphs and see if you can crank out the answer using the 3 methods that I just showed you earlier. So here's what I have. Here's my particle model, and as time goes on, the spacing gets further and further apart. For my position time graph, I got a curve. All right. For my velocity time graph, I've got a linear graph that's 5 meters per second squared as my slope, and I've got an acceleration time graph of 5 meters per second squared for 2 seconds. All right, well, I'm going to tell you, I do not know how to linearize this quickly on a test or exam or a quiz, so I'm not going to use this in calculating this answer. I can do it, but it's going to take a lot longer than I want to, so I'm going to use 2 quicker methods, my mathematical model of my velocity time graph, or the area under my acceleration time graph to give me the answer. So let's get going here. So there's my velocity time graph, and from here, just like we did with the previous problem, we can create our mathematical model. Y equals mx plus b. My initial velocity is 0 because I'm stopped at a stoplight, and then I start going. And from there, I cross that out. And so I have my 5 meters per second squared, but I went ahead and wrote this out as seconds times seconds to show you that this 2 seconds here is the seconds is gonna cancel with that one. And so what I'm left with is just simply 10 meters per second as my final velocity. Let's take a look at the area here. Well, the area is going to be my acceleration times time. Meters per second squared times seconds. And if you write that out on a piece of paper and use your dimensional analysis, you'll find that the area of an acceleration times time graph is going to give you your velocity. So there it is. So we've got a meters per second squared. The seconds cancels with one of these seconds, leaving me an answer in meters per second. That's what we call velocity. So when I plug in my numbers, I get 2 for my time and 5 for my acceleration, and there it is, 10 meters per second, which is exactly the same answer I got for the last way that I solved the problem. Now the third and final way I'm going to solve this is using my acceleration equation. Acceleration equals delta v over delta t. Final minus initial divided by final minus initial. Well, I've got an initial velocity of 0 because I'm stopped at the light and I start moving. And my time is also going to be 0. So I have my velocity over time is going to give me my acceleration. And when I do that, if I multiply both sides by t, the t's will cancel and it goes over there. So I get my acceleration times time is going to give me my velocity, or 5 meters per second squared times 2 seconds is going to give me 10 meters per second. So again, 3 different ways to get the same exact answer. I went ahead and I drew all of my graphs. From there, I determined which ones I'm going to use, whether it's going to be a linear mathematical model or the area under a curve, or I just used the equations that I know from practice problems. Okay, so you give this one a shot, and again, as always, pause the video, see if you can answer it on your own, and then start back and see if you can compare your answers with mine. All right, well, hopefully you got 22.5 meters per second. And this is what your graphs are going to look like. I'm not going to go over the problem because I've already done that twice already. But if you have any questions or need any tutoring, if you're living in the Phoenix area, well, you give me a call or give me an email at monroe.watson@gmail.com, and I can help you out as best I can. Thanks for watching.